Good afternoon and welcome back to our AP Physics 1 review sessions. Happy Monday. Hope you guys had a nice weekend. Hopefully, if you are on the East Coast, you are doing okay with the storms that just rolled through. I would like to welcome everybody back to another week of prep for our upcoming AP Physics exam. My name is Joshua Beck. I'm coming to you from Clayton, North Carolina. And today I've got a lesson for you about objects in orbit, so satellites, planets, things like that. Before we dive into that, though, I do want to discuss yesterday's question that I left you with. If you remember, or not yesterday, excuse me, Friday. If you remember from Friday, we had this scenario. We were talking about things experiencing centripetal forces. So those would be forces that are perpendicular to an object's velocity. So if you have an object traveling in one direction and then there's a force, which could be caused by a variety of different things. In this case, we have a force created with a tension from the string pulling. But if that force is at 90 degrees to the velocity vector, then it's going to cause this object to turn without any increase or decrease in speed. So that's going to create a centripetal acceleration. So the scenario that I had is I had this little toy car. I think down here in the bottom left, yeah, I've got a little clip. It's sped up. This is not how fast it actually went, but I've got this little clip of the car zooming around, and it's recording this force data as a function of time. And then we're going to come in and look at this. So I asked you to predict what you think this graph is going to look like. So let's take a look. The key to this physical setup is actually what's going on where the string attaches. Now you can see on this video clip, it's a little bit larger. If you look right over there, you've got this string and it's actually coiled around this pipe in the center. Now at any given moment, if I were to analyze the forces on this car, I'm going to have mg acting down, I'm going to have a normal force acting up, but in the direction or on the plane of this circular path, I'm going to have this tension. That's going to be that net force that's creating the centripetal acceleration. So I've got this equation up at the top, T equals mv squared over r. So at any given point, I'm going to have a tension that's creating a centripetal acceleration with a value of v squared over r. But some of these are going to be, there's something's going to be changing as this travels. The mass of the car is not changing. So this m value right here, that's not going to change. The speed of the car is not going to change either. I had this toy RC car, I had the thing pegged the whole time, so that's not going to change. The radius, however, will. If you look at the pipe, every time that this completes a lap, that string is going to be wrapped around that pipe one additional time. That's going to take the overall length of that string and shorten it. Then it's going to go around again, and it's going to shorten as it wraps around again and shorten again and shorten again. So that overall radius will be decreasing. So looking at this equation, this is analyzing Newton's second law for this car at any given moment. As r decreases, what would we expect to happen to t? Well, we would expect there's an inverse relationship between t and r here. So I would expect to see a decrease in r, and that should yield an increase in our tension. So I've got the data collection going. Let this thing go. Speed up the video. I didn't speed up the car. This is just the video going faster, 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 so we can get to the important part. And then we'll zoom in, we're going to look at this. Now this data is going to look pretty chaotic, all right? And I'll actually discuss why in just a minute. This data looks chaotic, it doesn't look as clean as we would maybe hope to see or expect to see. But what I'm looking for is a general trend. So I'm highlighting this, and I'm just picking a linear fit here. This actually wouldn't be a linear increase. We can get into that later, but I'm looking to see, is there at least an overall trend? Yes, my data is all over the place, up and down, up and down, up and down, and I'm going to talk about that in just a second. But overall, do I see a general increase in my tension? Yes, I absolutely do. That's what I would expect to see. My radius is decreasing, and as long as m and v are staying constant, then I should see a gradual increase in my tension. Now, why is this so hectic? Why does the data look like that? Maybe when you predicted this, you had like a nice solid line drawn with your pencil. Maybe it was straight, maybe it was curved, right? But you didn't have this chaos. So why does it look so hectic? Well, I'm going to show you a similar situation with a key difference. If you look at this video, look where the connection is. You can see I've got a carabiner here. So this is going to just rotate around this pipe. So this is not the original example. In this example, my R is going to stay constant. All right. So I'm going to let this video play. I'm going to let it go around. And on this second loop, what I'm going to do is I'm actually going to run behind this thing and run around in circles with my camera zoomed in on the force sensor so we can see what are the actual force values. I'll slow down the video. So right here, we see 2.177 newtons, 2.241 newtons, 2.279 newtons, 2.188 newtons. 1.99 newtons. Now keep in mind, this is not the first scenario. This is not coiling up around the pipe. This radius is not decreasing. This is a constant radius. And even at this constant radius, you're seeing this fluctuation in our force. Why? Because this is a real scenario. I've got imperfections in the concrete. I've got maybe imperfections in those wheels. Maybe the power going to this RC car is fluctuating a little bit. Maybe that force sensor is wiggling a little bit. It's just duct taped on, right? So I've got a lot of little variables in this real world situation, which is going to create some natural fluctuations here. Okay. Well, let me go back. After this, I'm going to switch over to a second clip, and you'll see in this one, I've just got a smaller radius. Basically, what I'm doing is I'm showing you what would just be a snapshot in our time interval of the original example, except now I'm keeping it at that radius and showing you that throughout that radius, you're actually going to, you could potentially see a variety of different forces. So here I've got a constant radius. It's a smaller radius. And here we've got 2.515, 2.490, 2.263, 2.279, 2.256. So you can still see some fluctuation even at now a constant radius. It's a different radius, but this radius is constant and you can still see this fluctuation. So what would that look like if I were to graph all that? Well, here, these are the first data points that I got. These were all the different data points that I saw when it was at that first radius. It's a pretty big range. How does that relate to our original data collection? Well, the original data collection, we were only at this radius for one moment. So we would only get one data point there. It could be all the way down here. It could have been all the way up here. Just after that, we could have been there. We could have been there. Just before that, we could have been there, could have been there, could have been there. So as we went through this range, we could see data fluctuating anywhere within that range. Now, as time increased, our radius decreased. So I picked a smaller radius and showed you the same example. And these were all the data points that I just called out to you. Pretty big range, right? So when our original experiment went through this radius, our data point could have been all the way down here, it could have been all the way up here, could have been anywhere in between. And then just after that, we could be somewhere in here as well. So we could get this massive fluctuation. All throughout here, we could have this fluctuation. So really what I was looking for, the reason why I put that line on my original data set is I saw all this chaos, but what I was looking for is, does it generally trend from a smaller tension to a larger tension? And we did in fact see that trend line going up. Now, would this be a linear increase? No, not exactly. The specifics of that are not crucial for this problem, but basically every time it goes around the pipe, the radius decreases by a set amount. But when you get closer, it's completing that loop around the pipe in less time. So that radius is actually changing at a quicker rate. So you'd have a little bit of curve to this true best fit. But I just wanted to see, does it trend upwards? And our data did in fact show that. All right, so let me know if you have questions about that. Again, the sort of take-home concept to that is, if I've got this constant speed and the constant mass, but then I start to manipulate the radius, what's the resulting tension going to be? All right. So today, what are we going to look at? Today, I want to look at circular orbits. In order to do that, I want to compare them to projectile, or objects that are considered projectiles, so projectile motion. Then I want to compare circular orbits to elliptical orbits. And then finally, at the very end, we'll connect this to angular momentum, something from several classes ago. So we'll start with projectile. Hopefully you watched the projectile video a few lessons ago, so I'll kind of breeze through this a little bit. But if we were to draw the path of this projectile, we would end up with something that's sort of parabolic. All right, that's not too interesting. What would be interesting is explaining why it's parabolic. So think about it. Can you explain how it's parabolic, or explain why this path would be parabolic? Take a second. Could you explain why this path is parabolic? See, we have motion on two different axes here, an x-axis and a y-axis. The horizontal movement, so that horizontal displacement, is increasing at a uniform rate. Okay, there's a horizontal speed. There's no acceleration, so that speed isn't changing. So that means my displacement is accumulating at a uniform rate horizontally. But vertically, that displacement is going to start increasing at an increasing rate. Okay, so the rate of that displacement is going to be our speed, and that's going to be increasing. Okay, so I have uniform motion on my x-axis, I have accelerated motion on my y-axis, so I end up with a parabola. Now, if I raise this projectile, I'm not going to go through this explanation, but a good self-check. Could you explain why the range of this projectile increases if h increased? If you can't answer this question, if you can't explain why, then please go back, check out the lesson from the 7th. Being able to explain why things change while addressing all the relevant variables is an important skill for P1, especially for the upcoming exam. So if you can't answer this question, be sure to check out the previous lesson. Today's focus isn't the explaining of this. Instead, we're going to compare. If this is my original path when my height was just here, now that it's going to be down here, we'd see our path would continue kind of like this. But today I want to increase this height, not just like a little bit, not just from, a couple books to a few more books, or from one table to the top of a bookshelf, or even out the window. I really, really, really want to increase this height. Okay, significant amount. So I want you to consider what's something that we wouldn't normally consider when looking at a projectile problem, but we might want to start considering as this range continues to get bigger and bigger. Think about what we might not consider in a normal classroom setting, or even outside, launching something on a field, but what would we maybe need to consider if we keep increasing this height and we start getting bigger and bigger and bigger ranges? Like, I don't mean a range of 5 meters, 10 meters, 100 meters. I'm talking massive ranges for these projectiles. If you said the curvature of the Earth, then you're on the right track here. Okay, so the range of our projectile would look something like this. And if we were to calculate this in a small setting, we would use our y components, our x components, right? Our frame of reference is nice and stationary here. But if we take into consideration the curvature of the Earth, we actually get a little bit of extra range here. Now, are these effects significant for projectiles launched in your classroom? No, please don't talk about the curvature of the Earth when you are analyzing just a normal projectile. A cart flies off a table, a ball goes down a ramp and comes off a table, a tennis ball is hit off a racket, something shot off of a cannon. Okay, none of these things are going to be affected by the curvature of the Earth. Okay, we are talking about heights that are significantly above the surface. So now we're basically talking about projectiles that are being launched in space. See, this is where projectile motion starts to transition into something in orbit. All right, now we're not really looking at a projectile so much, but instead we're looking at something in orbit. So what needs to occur for this projectile that I've drawn to actually be in orbit? Well, what does it mean to be in orbit? Well, if it's in orbit, then that means it's going to be a certain distance away from the surface of this planet. And as time passes, it's not going to come crashing down to the surface of the planet. Instead, we're going to keep this a set height above the surface of the Earth. So the path actually needs to follow this shaded blue line. If we could get the path to follow this line, okay, like this, then we could say that this object is in orbit. Now, in order to go from that initial curve to this one that I just drew along the blue shadow, this object would need to move faster. Now you might think, well, how is this orbit possible? Doesn't the object still have to fall? Isn't gravity still acting on it? Well, yes, of course it is. See, this was my initial vector. My initial vector pointed along this gray line right here. Are we still on that path? No, definitely not. So could you say that this object has fallen off of that path? Of course, it definitely has. Is gravity still acting on this? Well, yes, of course, that's the reason why it doesn't follow that gray line. If the Earth's gravitational field wasn't there, then it would just follow this gray line. So yes, gravity is pulling on it. Yes, it is falling towards the Earth. But is this path parabolic anymore? You see, with a regular projectile, our path is parabolic. That's because as this moves horizontally, the force of gravity is down. That turns its velocity like this, but the force of gravity stays down. See, with a projectile, the force of gravity is always acting down. But if you look at this path I just drew, this circular orbit that we've created, at this point, my velocity vector is this way, and my force is going to be towards the surface, or towards the center of the Earth ultimately. At this point here, there's my velocity vector, and the force is here. At this point here, there's my velocity vector, Oof, that's a mess. Sorry. It's hard to write on the edge of the screen. There's my force. Now, in all of these situations, I've got a velocity vector, and the force vector is still perpendicular, creating an acceleration that's perpendicular, creating a centripetal acceleration. That's what's making this follow a circular path. Now we've created a circular orbit. Now, in order to get this circular orbit, we have to have the certain ratio between the height and the speed. See, if I try and launch something from this particular point, but the speed is too low, what's the path going to look like? It's going to look more like a projectile. So without changing the height, how could I correct that? Well, let's look at where this lands. It lands right there. If I want it to be on this orbital path, the blue dotted line, where do I need it to land? I need it to land over here. Well, the only way I can get from this first path out so that it actually lands at this other path is if I increase the velocity. And so this thing can actually get further over. Now at every point along this path here, that's the force of gravity, that's the force of gravity, that's the force of gravity. It's always towards the center of the Earth. Okay, and the velocity is always like this. So I've got a force that's always perpendicular to the velocity. So when I get the right speed for that height, when I have the right ratio between the speed and the height of this thing, then my gravitational force actually acts as a centripetal force, never speeding this thing up, just continually turning it, turning it, turning it. You could think of it like it's trying to fall, but then the Earth is falling out from underneath it. And then the direction of the force is also shifting. And then you've just got this perpetual activity going on where it keeps trying to fall, but the Earth keeps falling out from under it. And then the force shifts and you keep recreating this and you get this nice circular path. Now, what if I tried to launch it from here, but I launched it too quickly? Well, then the path would look something like this. And now you're way outside of this orbit and you're actually at risk in this planet altogether. Or maybe not. We'll talk about what could happen in a few minutes. So what could I do if I wanted to correct this though? What if I want it to be on this blue orbit? Well, instead of landing out there after that time interval, after the same time interval, I instead want it to be right there. So I need to decrease the velocity so that my path can look like this. Now it's sort of falling along that blue dotted line, and now it's in circular motion. And now I've effectively put this in orbit. So I need to have the right relationship between its location and its speed. Depending on where it's located, it's going to require a different speed in order to stay in orbit. Okay. Now, so far we've been talking about height above the Earth or height above the surface of whatever planet, because that's a good connection between this projectile motion and then as I make it further or bigger and bigger and bigger, how can I eventually turn this into orbit? But is height really the variable I want to be using here? Not exactly. Here's a quick little illustration for you. In gray, I've got the height that we've been talking about so far. What I'm really interested in is the radius of the orbital path, this blue dotted line. What is its radius? What is that R value? Now I've included in red R of the Earth because this will come into some calculations. You'll see this, there'll be different R values, but in this case, the radius of the Earth is not that important to me. What matters to me is what's the radius of the orbit I'm trying to create. So it's not exactly the height that we care about. Instead, what it is the orbital radius and the speed. So I want you to try this. We're going to use Newton's second law to derive an expression. Oh, all right, two important exam. One, there may be multiple ways to solve certain problems. If they leave it open, then go with whatever way is most comfortable. Right? Some problems can be solved using forces or energy or momentum, right? There's a variety of different approaches. But if they tell you that they want you to answer using forces, or they tell you that they want you to answer using energy, or they tell you, I want you to answer this using conservation of momentum principles, well, then make sure that you're using the right methods. Make sure that you're showing them how you can use that set of physics principles to answer that specific question, right? It will do you no good to go completely a different route and say, well, yeah, but it could be solved this way. What they're trying to assess is, can you analyze this scenario from this perspective? So if it says use Newton's second law, well, then you better start with Newton's second law. Now it says to derive. Ooh, I still don't like derive. Derive is just solving something mathematically without putting the numbers in. So let's see what we've got. This object, right? M is the object in question. M is the mass of the satellite, the thing that's orbiting. That's the thing that's moving. That's the thing that we are analyzing. We are analyzing the forces on that and seeing if we can figure out what's the acceleration of that object. So the little m over here on the right is the mass of my satellite. Now we know that it's in centripetal, or excuse me, uniform circular motion because it's in a circular orbit. So I'm going to put A with a little c. It's a centripetal acceleration. So I can rewrite this side. Again, that's the mass of my satellite. This would be v squared over r. Now here's my orbital path. Here's my little satellite. There it goes. That's the velocity. And then I've got some force holding it in like this. What is the source of that? It's kind of like the car going around the pipe in the first example, except for now it's not a string. Oh, it's the force of gravity. Cool. So is that just mg? Mg, the force of gravity? Well, no. And we'll look at that tomorrow. We'll spend a little time talking about gravitational fields. mg would be the force of gravity on an object if it's at or near the surface of the Earth, where the gravitational field is equal to g, or 9.8 meters per second per second. See, if we're orbiting way out here, that is not what g equals. So we're going to use the universal law of gravitation. How can I find, under all circumstances, not just at the surface of the Earth, but anywhere, how can I find the force of gravity between two objects? And we use this equation, g m1, m2. In this case, I'm calling m, big M, the planet, and little m, the other object. That's going to be our satellite, over r squared. Now, I'm still just deriving. I don't need the numbers. I'm not plugging in the numbers. But I can look at this and I can cancel some things out. I see an r over here and an r squared, so I can cancel one of those. Then I see this m, and I'm going to cancel out one of these other m's, but which one is it? Remember, that m on the right side was the mass of the satellite. So that's that little mass. So what I end up with now, v squared will equal g big M over r. So that means v will equal the square root of that. Okay, I've just derived. Now, a little bit different way to approach this, especially in preparation for your upcoming exam where you're going to be typing and writing everything. Could you explain this? It's a similar type question, but rather than deriving it, I'm asking, could you explain why the mass of a satellite is irrelevant to its orbital speed? I don't want you to use this equation. This one right here, don't use that. You just derived that. I want you to explain in your words why the mass of the satellite is irrelevant. Well, ask yourself, at what point did I cancel out the mass of the satellite? We were still using it here. We were still using it here. The reality is, if you can solve these different problems, then you can probably explain what it is that you're doing in the first place. Okay, so I'm going to start writing basically what I would have done if it was a derivation. So the net force is equal to ma, where m is the mass of the satellite. I'm just explaining what was going on in my head when I did the derivation. So that means that the net force, which is due to the gravitational force between which two things? Between the satellite, little m, and the planet, which was big M. So once I get this set up, m will be on both sides of Newton's second law. And it can cancel. So little m will be on both sides of Newton's second law and will cancel. I've basically just described this part of my derivation and then this part where I canceled them out. And there, I've just explained why the mass of the satellite is irrelevant. Okay. All right, let's look at another practice problem. We're going to use this equation. Maybe they give you this expression, right? So we're going to use this equation. Doubled. Give you about 15 seconds to decide. How would the required speed to orbit change if the radius was doubled? Well, it's going to decrease, but we can be more specific than that. It's going to decrease by a specific factor. So my radius is going to double. So that'll be 2r, but that's in the bottom of the square root. So it's actually going to change by a factor of 1 or the square root of 2. Mathematically, that's 0.707. So V2, that's my new velocity, will be 0.7 times whatever my initial V was. It'll be about 70%. That's a decrease. Let's look at part B. How would the required speed to orbit change if the planet had twice the mass? So going back to our original, but now we replace the planet. I don't know how we do that, but let's just say we replace the planet with one with twice the mass. In this case, we would expect an increase in velocity. But is our velocity going to double? I'm doubling the mass, so maybe I have to go twice as fast to stay in orbit. Well, no, it's going to increase, but by a factor of how much? Well, let's look at the actual relationship and let's see what changes. G doesn't change, R doesn't change, but M does change. So that's going to be 2M. But that's inside the square root, so this is changing by a factor of square root 2. So that means that our new velocity is going to be about 1.4 times the original velocity. It's going to increase. It's going to be about 140% of what it was before. Okay, so this is how we can use this particular expression, and we can start to anticipate some specific changes. If we change one variable, what could change with the other? Now, in this problem, when I switched to the new planet, did I need to know the radius of the planet? Yes and no. No, I don't really need to know the radius of the planet. It's not part of my calculation. All I really need to know is if this is the orbit that I'm trying to create planets this big, well, then obviously I can't orbit inside that planet. So no, we don't really need to know the radius of the planet as long as it's inside that orbital radius. Here's a problem. I'm not going to go through this mathematically, but I want to give you just an example, just sort of a thought problem and how math could be used to support this. Could a projectile be launched? We said there's a specific relationship between height and speed. So theoretically, at any given height above the surface of the Earth or at any orbital radius, there's a speed that's going to allow something to orbit. So could a projectile be launched? Now we're back inside of our smaller scale. Could it be launched 1 meter above the Earth's surface and realistically be placed in a circular orbit? Now, obviously, some things are going to be in the way. There's buildings, there's hills, mountains, whatever. There's topographical features in the way. The radius of the Earth is not uniform at all places. If we could ignore any of that, could we launch this projectile? Well, we can use our previous expression. And in this particular case, I'm going to take my universal gravitational constant. I'm going to take the mass of the Earth. You wouldn't need to have that memorized. It would have to be given to you, right? This is just a thought experiment. And then the radius of the Earth, I would need to put it into the correct units because my universal gravitational constant is in terms of meters. And you say, oh, well, you're going to go 1 meter above the ground. Fine. So we'll put, if you want to be that specific, trust me, it won't change the end result here. This is going to be equal to about 8,000 meters per second. You say, perfect. Math says, yes, we could launch a projectile from a height of 1 meter and put it in orbit. How about physics, though? I see the math. I see the 8,000. What does physics say? Does physics say that's realistic? We've ignored the buildings and the mountains and the hills, but is 8,000 meters per second realistic? More than 20 times the speed of sound? Is that realistic? No, we've got incredible resistive forces at this location, right? Trying to launch something through our atmosphere at that speed is unrealistic. Now we get higher and higher, the speed necessary. As I increase this R value, the speed will get smaller and smaller. So that 8,000 number starts to decrease significantly the higher and higher we go. But also if we get high enough, we get out of our atmosphere. And so now we don't have to worry about this air resistance. So that actually makes the higher speeds possible. But could we realistically do it here 1 meter above the surface of the Earth? Math says yes, but physics, let's go with no, not realistic. Okay. All right, so let's talk about an object that is trying to maintain circular orbit, but failing to do so. We know that at a particular R, so this is a certain radius right here, from the center of this planet to the center of our satellite, that's a certain radius. So we know that at a certain radius, there's a specific speed that will allow this to travel in a circular orbit. But what if it's going slightly too fast? So if it's going slightly too fast, now I said slightly, I said not fast enough to escape. What does escaping mean? Escaping means that it goes so fast that it goes over here and it's completely gone, right? It's no longer in the Earth's gravitational field. That's not what we're talking about, okay? We're talking about just slightly too fast. Well, just slightly too fast means it's going to come off of this blue line just a little bit. And I'm going to draw a second point down here. And I'm going to say, oh, yeah, it's hard to draw. I'm trying. It's going to come over here and end up just a little bit off of this blue line. Okay. Now we're at a slightly different radius. We'll label this R2. Now I say here that the forces are internal. The forces that are acting on this satellite are internal, right? I've got an Earth satellite system. Together, I'm treating them as one system. Well, what's the force that's keeping this thing on a circular path? Or what's the force that keeps turning this satellite? Force of gravity, right? Well, that's the attractive force between the Earth and the satellite. So that's what our system is. So that force is coming from within our system. So if our forces are internal, then our total energy of our system won't change. So the delta E of our system is going to have to be 0. Doesn't mean that E equals 0. It means that delta E, the change in energy of our system, is 0. There's not going to be any change of energy, no exchange of energy into or out of our system. It's all going to stay within that system. But what happens to U? Well, what creates potential energy? Potential energy is energy that's stored within a system based on the location of the individual parts of that system, right? I take these two things. The force of gravity wants to pull them together. I pull them apart. Well, now they are moved or they're displaced from where they want to be. So there's energy that's going to be stored in that system now. Energy is stored in there because these are displaced from where they would naturally be. So based on the arrangement of these, I have a certain amount of potential energy. Well, if I move them further, now I have a different arrangement. So now I have a different amount of potential energy. And I've moved them further from where they would want to be. So I've actually increased the energy of this, the potential energy of this system. Whoa. But you said that the energy of the system can't change. You're right. So something else has to give. So what happens to our kinetic energy? Well, the kinetic energy has to decrease. So what's happening is it goes from the blue path to the red path. It's actually going to slow down. And now it's actually going too slow for this new orbital path. Bummer. Well, now if it's going too slow, it's going to start to fall back down below like we drew before. If it's going too slow, it's going to curve underneath the path. So it's going to fall below this, and it'll actually end up falling back down to this path. Now we have what we would consider to be an elliptical orbit. Got one radius that's a little smaller and one radius that's a little bit bigger. What if we did this the other way? What if it was going too slow? But I said slightly too slow. Look, if it's going significantly too slow, then it's going to crash. The path will look like this, and it'll crash. If I slowed it down even more, then the path would look like this, and it would crash. What would the path look like if the speed was 0? Crash, right? So if it's going too slow, then it has the risk of crashing, just like if it was going too fast, it had the risk of escaping. But we were just saying slightly too slow, and in this case, or slightly too fast in the last case, and slightly too slow in this case. So just a little bit slow. So we're going to start to fall, instead of on this blue dotted line, we're going to start to fall off of that. And where we're going to end up, I'll label it over here. We're going to end up at this. Let me try that again. You guys tried writing on a computer screen like this? It's not always easy. Ugh. There we go. We're going to end up on this path here. But again, all the forces at play here are internal. Well, what? Well, because it's an Earth satellite system. I've defined the system as both of these objects. The force that's acting on it is the force of gravity. That's an attractive force between these. That's part of the system. So that means the total energy of the system can't change, just like before. So delta E is going to be 0. Energy can be exchanged within the system. It can be converted to different forms, but the total energy has to remain the same. So as I've gotten these two objects a little bit closer, it's come a little bit closer to the surface of that planet. I've moved their location, and this potential energy is based on their location. So I've moved their location, I've put them closer to where they want to be. So that's actually going to decrease our potential energy. But that can't change the total energy of our system. That has to stay constant. So something's got to give, and we actually get an increase in kinetic, which should make sense. As this thing falls closer to the surface of the Earth, it's going to pick up speed, except now it's going too fast for that green orbit. So now we're back to our earlier example. What if we go too fast? We've got our orbit here. We're going to come flying off of that orbit. We're actually going to fly above this green line and end up right back to there, right back to our blue line. Again, we've got one radius here. We've got a different radius here. And we once again have an elliptical orbit. So if we're going, so if we have a satellite that's orbiting a planet, we can approximate it as uniform circular motion. Right, there's a specific speed in order to maintain that uniform circular motion. It's based on the mass of the planet, not the satellite. It's based on the mass of the planet and then the radius of its orbit. And I showed you that derivation, how to find that exact speed required to maintain that circular orbit. Okay, so we can derive that from Newton's second law. Make sure you can also explain why the mass of that satellite doesn't come into play here. Okay, so think about how would you derive it, and then how would you just explain what you're doing. Now, if the speed is slightly too fast or slightly too slow for that orbit, then it can't stay on that particular path. Remember, it's a specific speed for a specific orbital radius. So if the speed is too fast or too slow, it will start to move to a different R, so to speak. That'll require an energy conversion, okay? Exchanging some potential energy or converting some potential energy into kinetic or vice versa. Now that could lead to a new orbit. It would be elliptical. Or if it's way too slow, it could crash, or if it's way too fast, it could escape. Our elliptical orbit, just to kind of summarize, is really just something switching between one radius and another radius. Okay, and we got this path as it goes. Now, it's usually not going to be this extreme. In most cases, it's not this extreme, but if I were to draw it too similar, then you wouldn't notice the difference. So I've got this exaggerated on all these examples. Now, what I want to end with today is instead of just looking at the motion of the orbiting object. So now we've been focusing on just the satellite itself. We said, oh, the satellite is in circular motion because there's a centripetal force. Oh, the satellite is going up or down. Now I want to look at this whole system as one object. Okay, we've talked about the system, but now I want this system as one object that's rotating together. Okay, it's like if somebody was on a Ferris wheel, for example, you could look at that person and you could say, oh, look, that person is in uniform circular motion as they go. And then somebody else could say, well, yeah, that person is just one piece of the giant Ferris wheel. And that whole thing is rotating. That whole thing has an angular velocity and angular displacement, has angular momentum. Both of you would be correct. You're just looking at it from different perspectives. Am I pinpointing that one object and saying, oh, what's its linear speed as it moves? Or am I saying, no, it's all one part of a giant Ferris wheel and the whole thing is rotating and everything on that Ferris wheel has an angular speed and an angular displacement? So you can look at something in orbit as the giant system. Now, it's not filled with solid stuff in the middle, it's open space. So it's just one mass here and one mass here, but that whole thing is rotating like this, or rotating like this as it goes in orbit. Now, if you picture it that way, this leads me into my practice problem. Okay, I will go over this at the beginning of our video, or beginning of our lesson tomorrow, review lesson. But I want to leave you with this. What happens to the linear speed of this Earth when it's at its closest point to the sun? Justify your answer. Considering the entire system to be in rotational motion, like I just described, with the sun at the center, does the angular speed of the system increase or decrease when the Earth is at its closest point to the sun? Justify your answer. And now I'm telling you the forces acting on the sun and the Earth are not capable of changing the system's angular momentum. They weren't capable of changing the total energy in the system. They're also not capable of changing the system's angular momentum. Right? Greg talked about angular momentum a few classes ago. Explain why these forces are not capable of changing the angular momentum of our system and how that condition is even possible if this angular speed changes the way that you described in part B. All right, I'll leave this up here for another second. Feel free to screenshot this if you need to. This is what we're going to start class off with tomorrow. Okay. In the meantime, if you have any questions about today's lesson, feel free to reach out to me on Twitter. I'll be talking to you tomorrow about gravitational fields, gravitational forces, and then Greg will be taking over again on Wednesday and Thursday, and then I'll be back on Friday. So we're looking forward to an eventful week with you guys. I hope this has been helpful. We are still enjoying this very, very much. We appreciate the feedback. We appreciate all the questions we've been getting. So I'm going to leave you with this problem. I look forward to seeing you tomorrow. And then I'm going to hand you back over to Greg after that. So enjoy the rest of your day and hope you guys have a great week.